Hello and welcome to the Engineering Dynamics Course Companion. This is class 24, the last class of the semester with kinetics of rigid bodies, and we're going to deal with impact of rigid bodies. Okay, so let's go to the bottom line up front. You can skip all this and go to the example if you go to the table of contents down in the description below. So the impact of a rigid object at any place besides its center of mass will cause an exchange of angular momentum and cause the thing to spin, right? And so we have a collision that hits, boom, and we start spinning, right? That just kind of makes sense. A ballistic pendulum is a really common type of problem where we take a look at this. And what can happen here is that when they say ballistic, because maybe a bullet will hit an object and cause it to shift and move, and we use that to estimate, go backwards, and figure out what the bullet's velocity was by way of doing this arrangement. When we're going to do a problem, like if we go back to class 12, when we did particle impacts, or even class 11 and 12, we did particle impacts. When we did class 12, we had normal and tangential coordinates that we had to set up when we had oblique impact of things, right? When things hit each other coming at maybe different velocities, we had to take the point of contact, and we drew it through the center of the pieces, but now we want to kind of like have it's not going to be through the center of the pieces, but about like through the 2 points, through the point of contact right there. And we still need to do that when it's a rigid body. So we need to create that normal and tangential coordinate system and then separate out those bodies. And when we use the coefficient of restitution, it needs to be with respect to that location of impact, not at the center of masses, right? So the example that I use right here, or one example that I use here, are like if someone were to throw two footballs, and let's pretend these things have perfect spirals that are coming towards each other, and they hit at some point. Let's say, okay, well, this is a baseball, but it hit at some point, and you could just see that they're going to start spinning away from each other. We just kind of know that. So looking at this impulse momentum diagram here, where at the impulse stage, we can see where we have this normal coordinate system that's being placed right there through the point of contact right there. And that's where the equal and opposite impulses are going to take place, and they're going to cause this thing to start spinning outwards right there, right? So we have, we could, depending on where we were going to make some type of reference, we could have these distances that are going on here, and then we would know that we would have both, and I don't know why I don't have the other one. I think I also need to have IB omega 2, and this should probably be A2, and this should be B2, but they're probably going to be equal and opposite. And by the way, let's see, A looks like it's going counterclockwise, so that one must be clockwise. So if for instance you were just taking about the center of gravity, that would be like 0, and this would be 0, right? And this would be 0, and this would be 0. So basically what you would be saying is that those two things would have to be equal to each other afterwards. It's simple. But now if you were going to take a ball separate by itself, then you would have to have the impulse, right? The impulse of this thing would need to be included, but you could take the y direction of this separately and only do the I direction. The I direction, but the I direction. In this case, we call it the tangential direction, and you could see that the velocity in the tangential before equals the velocity in the tangential afterwards. Okay, so here is a ballistic pendulum, where we're going to start out with a 0.25 ounce bullet. It's traveling towards a 10-pound block that's supported on a rigid rod, and the rod weighs 2 pounds. And it starts at rest, as shown, and the block is 12 inches high and 3 inches thick, 12 inches high, 3 inches thick. And the rod is also 12 inches long, and its width doesn't matter. It's slender enough that it's not going to matter. And the bullet embeds in the block, and the center of the block then rises to a height that's 1 inch higher than it was before. We want to determine the speed before it hits the block. Okay, so we call the block state 2. Right, so that's because we're going to have like several things taking place. But let's first start, and this is often the case, we want to kind of like work a little bit backwards, and because we know where the thing ends up, we can kind of we could then use energy, conservation of energy, to find what its velocity was before, just after the bullet hits the thing, just after the bullet hits and embeds the velocity of the block together. So we could do that and call those states 2 and 3. We could set up like a datum for that, and we can call the center of the block where it gets hit. We could call that E, point E, right there. So we needed to give that a name. So we could figure the distance for point PE to the pin. We could say that it's 1.5 feet. So what we could do is we could also find out what the mass moment of inertia of the block, the block assembly and all of that. We could find that with respect to point D up here. That'd be a good thing to know. And let me double check something. It appears as if, yeah, okay. So here's the block right there, right? So here's the block right there. And here we're using the parallel axis theorem to bring it up to point D. And then here is the rod, CD, and here's the rod, and it's slender, so it's just 1/12 and mass times the length of the thing. And notice that I'm taking, I'm dividing the pounds by 32.2 to get that into slugs, so that gets us the mass. And then also I'm taking the parallel axis theorem to move the rod up to point D. So here's what my total mass moment of inertia is of the whole thing about the pivot point for the rod, right? Okay, so now what if we included the bullet, because the bullet does embed, but remember it's only like 1/4 of an ounce right there, and I looked that up to find whether that was true. We would also add in okay, so this is the I that we just calculated, but we also want to add in the bullet as a point mass, and so take its mass and the distance, and you'll see that it has a very small effect, right? So all right, so and then we could also figure out what the angle that this thing reaches, right, when based on, okay, so it has moved up 1 inch, so there, right there. So that ends up being this theta that it has moved is 19.19 inches. So the maximum height of the center of the rod is therefore, okay, so we know the center of the rod of this block is, but the center of the rod instead, this thing moves, and we could have done probably law of triangles right there, right, similar triangles to have gotten that, but we use the angle instead, and we get that it moves up 0.3333 inches right there, right, repeating 3. All right, so now we have the conservation of energy at state 2 as the datum, and so between states 2 and 3, we have, this is what the momentum, the kinetic energy at state 2 is going to be. It's going to stop, and it's going to turn into potential energy of the thing rising, okay? So it's stopped, so that's why that kinetic energy is there. And then this potential energy is the datum, so that's why that's 0. And we're able to find what that angular velocity is going to be right here at state 2, right? So that's of the entire thing together. And by the way, I'm including the bullet as part of this. Now we do an impulse and momentum diagram, and we can see what happens when, okay, here, so the bullet has all of the momentum here in the beginning, and then an impulse takes place, and that's the equal and opposite there, the bullet and the block back and forth on each other. And then at the end, it just has this angular momentum But by the way, and we don't need to use the center of the thing because we are, excuse me, because we've already included it by way of including the mass moment inertia about point D. So we have the conservation of angular momentum taking place, and you can see it's quite simple, right? We're taking it about D, right? So that's the point about which we're taking it. So we have this mass times velocity times a distance, right? So that's that distance that's right there, and it ends up with that moment of inertia. And so we go ahead and put those values in, and we're able to figure out what that velocity is going to be right here. 1,878 feet per second is the answer. And maybe we want to find that in miles per hour because that'll make us, we'll understand it a little bit better. Now, I went ahead and I included example 24.2 in here as well because it's an interesting add-on to see, okay, so before the bullet embedded into the block, but now let's say it ricochets off and it has a coefficient of restitution of 0.4, right? We want to determine the speed of the bullet before it hits the block and its ricochet speed. So we want to update everything. So its conservation of energy right here is all well and good. But the only difference that's going to happen here, and we should actually probably include that here. Now that I'm thinking about it, we might actually want to include the inertia, right, of the, no, we're fine here. Because this, yes, the block moves to the same position. I'll take it back. We don't have to worry about the bullet because state 2, the bullet has bounced off, right? It's just after the bullet has bounced off. That's when state 2 and the block and rod together move as one, and they start to swing, and they have an angular velocity, and then they're eventually going to stop at state 3. Okay. So now we update the impulse and momentum diagram. And here in this, we now have to include that the bullet's going to bounce off, right? So if we write off this, you'll note that we now have, and I decided I make the bullet pass that direction. By the way, if we find out the end that the bullet's going the other direction, it could possibly happen. I mean, you got to appreciate that we're really simplifying this scenario right here. The bullet could want to keep going, bounce and hit onto the thing and just lose some of the velocity here and then tumble down and hit the ground. Right, but let's just treat it as an idealized state. So, but you can see that negative right there is because this thing is going in a clockwise direction. So we have all the other things taking place that we'd expect. So we go ahead and put those in there, and now we have 2 unknowns. Right, we have this bullet initial, and we have the bullet final velocity. So there you go, equation. I call that equation 1. And interestingly enough, yeah, okay, so I got out them. All right, so now what we're going to do is we have to apply the coefficient of restitution because there's one equation and 2 unknowns. So we want to call that point E, and we want to take a look at the relationship of the velocity to of the body, right? So let me go back up here and just take a look if I can. All right, so make sure that that position, that's E right there, and we need to know what the localized velocity is because that's what we need to use in the coefficient of restitution answer because that is the velocity that's normal to the impact zone. So the kinematic relationship of the angular velocity and the velocity at E was this one right here. Okay, so that's the velocity after the impact, right? So localized on the block. And the coefficient of restitution can be written out this way. Remember that it's the relative velocity of these two, but they get reversed, right? It's the negative relative velocity relationship when you're using that. Let's see, get rid of these because this in the way. So we have this this velocity at state 2, and we have 0.4 times, and this thing starts at rest. So now we have a second equation, right? So we combine that with equations 1 and 2, and we're able to find here's the ricochet velocity, and it shows it as negative. Therefore, we're going to predict that the bullet's going to keep on going. It keeps moving to the right, but the block is going to still be kind of in the way. So it's probably going to end up dropping downwards in reality. But here is what the velocity, the initial velocity is, which is considerably higher right here, right? So 2,130 miles per hour. Right, so it's almost better for us to, when doing this, to go ahead and let the bullet hit and stick, or make the block out of something that the bullet will stick into, and that's generally what will be done. So there you go. There's the answers for you. So that's the last example out of the book, out of the two books, parts 1 and part 2. For more examples, check them out. The Engineering Dynamics Course Companion Part 1, that deals with particles and covers both kinematics and kinetics for particles. And then for Part 2 is rigid bodies. Right here, right? Am I got the right one? Yeah, Part 2 is rigid bodies, and we also deal with kinematics and kinetics. This is published by Morgan and Claypool, and you can click to the links below to go to the publisher's website where you can purchase them, or you can go to Amazon and look it up and you can find it. You subscribe to the channel. I will plan to be updating some of these videos and also increasing some of the content, probably in response to questions from my students and from people out there. Newt Dog, the cartoon, and Wormy, they're trademarks of Edward James Deal, whoever that is. And I should also point out, these books also have a bunch of extra problems in them in the end. Each one has a collection, and I think of these as exam prep problems, like maybe the degree of complexity and time limit that you might find in a problem that a professor might give you. So these are extra opportunities for you to try to solve. And I provide the answers, but not the solutions. And my purpose in that is, whereas I could just make this thing a longer and longer book, the really important thing that you want to do to be able to succeed in dynamics is to solve problems yourself all the way out without taking a look at the solution. And unfortunately, that's not a pleasant thing to have to do. So many students will just go ahead and read the solution, or they'll watch the video and they'll absorb it and then believe that then when it comes test time, they'll be able to just sit down and start working through it because they totally understood. They were able to follow the logic. It made total, complete sense to them. But then when approached and having to see a problem and work it for yourself, it's much, much different than seeing the solution to something and understanding the solution. It's the act of trying to work through and problem solve. And I've tried to emphasize that along the way, or trying to emphasize the thought processes while you're going through and solving these problems. And I hope that you will take these problems that are at the end of the book, out of each book, and organize to tell you where they fit within the scheme, and try them out yourself and try to work them through until you get a problem. I want to thank everyone that contributed to help me along the way as I've been teaching dynamics for a number of years, and the acknowledgement in the book. I definitely do that. But I want to thank you for spending this time with me, and I hope that this has helped you as we are your course companions during this difficult time. So thank you very much.